A few months ago I published this video where I put together some geometry explaining how both polar regions can each observe a 24-hour sun thanks to a 23.5 degree tilt and the Earth being a globe. So in this video I'm going to go a step further by taking some well-established things that we say about the globe model, and I'll use them to somewhat accurately predict the amount of sun hours any place on Earth can expect to receive from sunrise to sunset on any given day of the year. To do this then, I'll be using 6371 kilometers for the radius of Earth. The distance to the Sun is at 149.6 million kilometers. The angular size of the Sun is a tad more than half a degree, and that's at 32 arcminutes, or 16 for the semi-diameter. And refraction at the horizon is about 34 arcminutes. And what that means is that the Sun can be geometrically hidden, but fully visible at the same time. Now there's quite a bit going on here, so let's take a minute or two to explain what we see. We have a day side in blue and a night side in black. This is the geographical position or GP of the Sun, which is a point directly overhead in the direction of this vector, and it's 149.6 million kilometers away. We have 35 locations scattered around the globe, and we can select any of them using this slider. Location 21 is for Philly. These are the stored coordinates. That's this point here. These two vectors are tangent to the curved surface. The white one always points in the direction of the North Pole, and the yellow one always points in the direction of the Sun's GP. And it's these two vectors that allow us to measure the heading. There is a third vector here that always points to the Sun out in space, but it's currently pointing into the ground, which is why our altitude reading is negative. We have this day length output here, which is reading 15 hours and 33 seconds, and it's currently in green. This reading could also be in yellow, and we'll talk about what these colours mean in a moment. Over here we have this declination slider, and this allows us to select a different time of year. Right now the Sun is above the Tropic of Cancer. We can move this along. Now the Sun is over the Tropic of Capricorn, or we can opt for these simple presets over here. So how do we go about estimating the length of day? If we can take a snapshot at solar noon, then we can visualize an arc of a latitude circle that covers half of the day for the observer location. And determining this angle means we could work out how much of the 24-hour period was day and how much of it was night. Now it's pretty easy to get GeoGebra to measure this angle for me, but I thought it'd be fun to go the math route. And this is what I ended up with. Now that we have our angle, what do we do with it? Well, if we rotate our observer point around its latitude centre by that angle, we can then reposition the Sun back to a time where the observer location sits directly on the terminator line, i.e. sunrise. But this is not the type of sunrise we want. Notice the altitude angle to the centre of the Sun is practically zero. That means half the Sun can already be seen above the geometric horizon, and this daytime calculation, which is in yellow, never actually accounts for the Sun completely going down, and it doesn't take into account the lifting effects of atmospheric refraction at the horizon. And that's why this click to adjust button has popped up. What this button will do, it will adjust the Sun's position backward in the case of sunrise, or forward in the case of sunset, to a place where the altitude angle is 50 arcminutes less than its current value. So why 50 arcminutes? Well, the semi-diameter of the Sun is 16 arcminutes, and this would take us to a time when the upper limb of the Sun is in line with the geometric horizon. The other 34 arcminutes is there to negate the lifting effects of atmospheric refraction. Now that we can see that the altitude angle is negative 0.833 degrees, that's 50 arcminutes, and our adjusted daytime length here in green, shall we compare this with what Time and Date has to say on their website? Right, we have 9 hours 55 minutes and 58 seconds. They have 9 hours, 55 minutes and 59 seconds. Only 1 second out. I don't think it's going to get much better than that. It can only go downhill from here. We have 62 degrees east-northeast for our heading, so do they. What else? Solar noon. We have a heading of 0 degrees, which is the same as 360 north. We have an altitude of 33 degrees, and so do they. Sunset. Let's adjust that as well. 9 hours 55 minutes 58 seconds and a heading of 298 west-northwest. Okay, let's try another one. We'll try Capricorn this time. And let's pick a place. New Delhi. Sunset or sunrise, doesn't really matter. Let's go sunset. Click to adjust. And we have 10 hours, 19 minutes and 1 second. Let's see what time and day has to say. Okay, so they have 10 hours, 19 minutes and 17 seconds. This time we are 16 seconds out for the whole day. That's 8 seconds either side. We have 244 heading here. They have 244 west southwest. Let's try solar noon. We have a heading of 180 south. So do they. Our altitude angle is 38 degrees, which matches theirs. And what else? Sunrise. Okay, 116 east southeast. Yeah, pretty good. 16 seconds out that one. Should we try one more? Where should we go? Yeah, let's go to Newfoundland. Hopefully I pronounced it right this time. That's St. John's. And we'll pick a random date. Let's pick a random date as well. Let's say April 23rd. Let me look that up. Okay, so that is 12.744 degrees declination. Let me just change that. 12.744 degrees. And if you got yourself over to that latitude on that day, on the 23rd of April, you'll find that you'll have no shadow at some point. So let us go to sunrise. We'll adjust it. And we have 14 hours, 5 minutes and 2 seconds. Let's see what time and date says. So they have 14 hours, 5 minutes and 47 seconds. So now we're 45 seconds out. Still within a minute. We have a heading. Ours is 70 degrees, east-northeast. They have 70. Solar noon. We have 180 south. And the altitude is 55 degrees. So is theirs. Sunset. We have 290 west-northwest. Yep, so do they. So all in all, not too bad. It goes to show that a light in the sky can tell you something about the shape of the ground after all. And this is just a simple model working off a few basic parameters. And it can only be made more accurate if more things are taken into consideration. Alright, if you can stomach it and you want to stick around, I'll quickly run through this script. This is the working part of it really. I've got rid of all the text stuff, so you can't see that. Tropics, we'll start here. That draws our 3 circles. Polars, that's the Arctic and Antarctic circles drawn. Pole, that's the North and South Pole points. D, that's the distance to the Sun, so you can work out that the Earth has a radius of 1. Sun, that's just a point out in space. That uses D. It uses these 2 sliders also. And that is just a point. It's not a sphere. It doesn't have a radius, no dimension to that. S is a unit vector to the Sun, and the GP will use that vector. So that's how we draw that point there, using that vector. Terminator is this purple circle, and that has a radius of 1 also, and it uses S to draw it. B, if we look underneath here, so the bottom part of the terminator, that's point B. And we use point B to draw the 2 surfaces, or I do anyway. Let me know if there's an easier way to do it. What else do we have? Locations. Ugh. This is what I painstakingly typed out. So that's 35 locations, and this is all the names of those locations. P, that's this point here, currently Edinburgh. So that's location L, and L is 7. So if you go to our locations, you should see number 7 is Edinburgh. Lat is the name I've given to the latitude of this point. Great circle, that's a circle of radius 1. Doesn't really save much point, that great circle. It just lets you see that it is a straight surface path to the sun's GP, or in the direction of the sun. C for circle. Right, that is just a circle that gives length to these vectors here. It also ensures that they stay tangent to the surface. So if we look around there, you can see that's a tangent circle there. N is the North Pole vector, V is the direction vector, and U is the altitude vector. W is just this one here, it doesn't really do anything. It just looks good when we have these two pointing in the same direction. Where are we next? Alpha. Alpha is the heading angle. So that is between this white one and this yellow one. Altitude angle is the angle between the yellow and the black one. Half angle. So the half angle is what we worked out. That gives us the angle for the half day length. Seconds, well, that uses the half angle to give us the geometric day length. Seconds prime. This gives us a time in seconds for the day after we've moved the sun's position. And A gives us locations we can use when we're adjusting the sun's position. So you might recognize the cosine rule in here. And that's pretty much it.